Hello everyone, and welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today's video is going to be more of a vlog kind of video. That's mostly because I was working on a project and I thought that I designed everything right. And surprise, surprise, I have some problems. I cannot finish the project right now, so I cannot come to you and show you fully finished device. However, it's still worth making a video and still worth presenting my efforts so far, my progress so far, so that in the future I will simply come and mention the solution for the problem and continue working from there towards finishing a full device. Now, what we're talking about is very simple. I'm just gonna make a long story short. Somebody a few months ago donated an Arduino Uno to me. He had one and he just did not needed it anymore. An original one, not that it matters so much, and in perfect functioning. So I received this Arduino, and initially I had nothing to do with him, but sort of at the same time, in the last few months, I came across the situation when I just need to make multiple measurements at once. And I pretty much need to use all my multimeters. I don't have that many of them, only 4, 5 if you include the clamp meter, which is typically used for measuring currents, but it can measure volts and ohms as well. Anyway, I thought, why shouldn't I think about building with this Arduino a 4-channel multimeter? So that I have an actual device that is able to measure 4 different things, and so that basically I don't have to occupy so much space, because when you use discrete multimeters, the more you use them, the more you basically fill your workbench, the space on your workbench. And it becomes harder and harder for you to work. You have a lot more cables around, all those multimeters take space. You also have to make sure how to properly align them so that you can see them easily, because if you put them on a wrong angle, you would have to, bend on top of them or something. Anyway, I thought, why not just think about a 4-channel multimeter with Arduino that is able to measure some voltages, some currents, not more. I don't care about resistances, capacitances or other things, just voltages and currents, and having the possibility of measuring multiple things at once would give us some extra possibilities that would not be available by using single multimeters, such as measuring the efficiency of a power supply or of a DC to DC converter, because you can at once measure input voltage, input current, output voltage, output current. Anyway, this was the idea, and the idea was backed by the fact that it was a possibility made by the fact that an Arduino Uno has 6 ADC inputs. Now, 2 of them are actually in common with the E2C, I2C, or I don't know how you call it, interface. So 2 of them we will not be able to use. However, the remaining 4 of them can easily be used for measuring voltages. And we have a whole bunch of other digital pins that can be inputs and outputs as well, but we will care more about inputs. So yeah, I thought, why not? This project shouldn't be impossible. Now, from it shouldn't be impossible to it's easily doable, that's a difference. But anyway, I started thinking about what I need, and needless to say, I need a circuit that will be basically a front end, one for each channel, because the Arduino is powered by 5 volts, and at the same time it can accept a 5 volt full scale range on its ADC. The ADC is 10 bits. So basically Arduino himself, without anything else, can measure positive voltages from 0 to 5 volts with a roughly 5 millivolt resolution. In reality, it's more like 4.88 millivolts, but let's not get lost in the smaller details. Let's say 5 millivolts, okay? So that would make a pretty good voltmeter, a pretty good multimeter. Yeah, so, but of course we cannot just connect a voltage to the Arduino input ADC pins, because one, we might have negative voltages, and two, we often have more than 5 volts that we want to measure. So we need a circuit that will somehow do something with that voltage that we want to measure in order to bring it down to a maximum of 5 volts, and in order to tell the Arduino, hey, this is a positive voltage or this is a negative voltage, and stuff like that. And on top of that, I wanted to have an auto-ranging multimeter, because yeah, especially when we're having 4 channels, we really don't want to have to turn so many switches just to select the proper voltage range or current range. That wouldn't be a nice thing to have. An auto-ranging multimeter would be a lot better to have, and theoretically it shouldn't be all that difficult to accomplish. Now I will show you the schematic in a moment. I will go through the whole circuit. It's quite elaborate. It's not difficult. It's sort of like a puzzle made from multiple pieces tied together. So I will go through the circuit step by step, and I will show you. But first of all, allow me to give big thanks to PCBWay for basically making this project possible, because this front-end circuit is quite big in terms of number of components. As you can see now on the screen, this green PCB is one of the front ends. We actually need 6 of them, 4 for voltages and 2 for currents. Anyway, I'll get into those details later. Creating such a PCB at home would not be impossible, but would definitely result in much bigger board for each channel individually, and would require a lot more work to do. So yeah, PCBWay was agreed to sponsor this video and basically help me create these PCBs by not just creating the PCBs, but also planting half of the components on them, semi-D components, so that I can bring the dimension of the PCBs down, and so that I can make my life easier. So they offer both PCB manufacturing services and PCB assembling services. They also offer injection molding, 3D printing, CNC machining services if you would like to build a custom plastic case or a custom metal case. And the whole process is quite easy. You just create your project, in your favorite design software, export all the necessary files, upload the Gerber files and bill of materials, and then one of their professionals will basically analyze what you've done, will search for the components, and will come back to you giving you a quote about how much those components will cost. And then once you agree and once you make the payment, the whole manufacturing process will become very easy and quite fast. The PCB himself will be ready in as little as 1 day, and the whole manufacturing will be done in less than 2 weeks. So all in all, it's a nice solution to think about whenever you have to deal with larger projects that would require a lot of time and energy for you. Like I said, thank you very much PCBWay for sponsoring this video. And now let's get to explaining how this circuit works, or at least how it should work, what does work, what doesn't work, and where I will need to do a better job and fix it in the future. So, like I said, we need to feed a positive 5 volts voltage to the Arduino no matter what. But on the input, of course, we want to have a wider range of voltages, and we also want to have negative voltages. So it becomes pretty clear that we can apply 1 to 10 or 1 to 100 ratio of division, so that if we have a maximum of 50 volts, we can divide it by 10 and have the 5 volts that we need for the Arduino. If we have a maximum of 500 volts, then we basically divide by 100 that voltage, and we will have that maximum 5 volts for the Arduino. So we start by essentially bringing down the voltage through a resistor divider. I'm showing you now the block schematic, and I will go in a moment and I will show you the actual electronic schematic. But it's a lot easier if you understand how this works on a conceptual level, and the block schematic is just that, a conceptual representation of the circuit. Okay, so whatever voltage we have on the input, either positive or negative, up to 500 volts, we feed that into a voltage divider. Now in reality, this voltage divider is a bit more complex than that. There are actually 2 voltage dividers made with multiple resistors, so that we can mix and match basically resistors, so that we can have an accurate division ratio. But anyway, skipping over that detail for the moment, we have basically an attenuator, right? A voltage divider that will divide the voltage down to by a factor of 50. Okay, 1 to 50 division. This means that 500 volts maximum voltage will be brought down to 10 volts, 50 volts brought down to 1 volts, and 5 volts to 100 millivolts. Now, because we want to have multi-channel also multimeter, and we want these channels to not have a common ground, because that would basically be a problem. That would limit our possibility to take measurements, or if we forget about it, we can even damage the circuit by accidentally making a short circuit in the circuit that we're actually trying to measure something. We want this voltage divider to basically be a differential one. Okay, so we have essentially 2 voltage dividers that go from each pin from the input to the ground of this particular circuit. This means that at the output of this voltage divider, we will not have 10 volts, 1 volt, and 100 millivolts. We will actually have 2 voltages that in most cases will be equally centered around the ground, and so we can say that we will have a plus minus 5 volts, or plus minus half a volt, or plus minus 50 millivolts. Now, having two voltages is not an ideal situation. We need to be able to work with, we need to have just one voltage, because that's the way we can work with that particular voltage and do all the other processes, or all the other things that we need to do. So we need to convert these two voltages back to one, and for that we use basically an instrumentation amplifier, which is essentially just a differential amplifier with buffers in front. Now, concerning the instrumentation amplifier, you can search on YouTube and you will find, or even articles on the internet, you will find articles or videos explaining to you what an instrumentation amplifier is. So I will not make a dedicated video for that. There have been others before me that have done that. Safe to say that the instrumentation amplifier basically takes those two voltages, calculates the difference between those two voltages, and spits out on its output basically the difference between those two voltages, right, as a voltage referenced to the ground of the circuit. Now, I keep saying a difference between those two voltages, but when one of those voltages is negative and the other is positive, basically their difference will be exactly like adding those volts and having a new voltage with a magnitude equal to both input voltages, and the sign equal to the sign of the first voltage. So if the first voltage is positive, then the output will be positive. If the first voltage is negative, then the output will be negative. So this will make it so that instead of having plus minus 5 volts, we will actually have 10 volts on its output. Instead of having plus minus half a volt, we will have 1 volt. And instead of having plus minus 50 millivolts, we will actually have 100 millivolt on this instrumentation amplifier's output. And this is the voltage that is both within a small range of values that we can easily work with, because this entire circuit works with plus minus 15 volts, and 10 volts is well within the common mode range of all the operational amplifiers used here. And at the same time, it's only one voltage, so we can easily work with her. Whether she's positive or negative matters less at this point in time, okay? So this instrumentation amplifier will also require a bit of an offset correction, because when we will have small voltages on the input, here we will have very small voltages on the output of the instrumentation amplifier, and input offset voltage of any op-amp that is, you know, it's not a so-called zero drift or auto zero. Any input offset voltage will be significant and will basically constitute an error at the end, and we want to minimize that error for as much as possible. So we will also have an offset correction circuit that will apply a correction to this instrumentation amplifier. Now, once we have this voltage here in the middle, spit out by the instrumentation amplifier, we will need to do several things with that voltage, and we will need to pass it down to basically two different circuits that will do two different things with that voltage. First of all, we will need to bring whatever voltage we have here, we will need to, as a maximum, right? We will need to make it so that on the output we have 5 volts maximum, no matter what. When it comes to the 10 volts voltage, we will just need to attenuate it, but when it comes to the smaller voltages, we will need to amplify them. So next, after the instrumentation amplifier on the main chain, There is another amplifier with a variable gain that we will set based on certain parameters I will discuss in a moment. So when we are here, when we measure voltages between 50 and 500 volts, this amplifier will not really amplify the signal. It will have a ×1 amplification, so unity gain, and whatever voltage is on the input, either negative or positive, will be thrown as it is on the output. Okay. If we have voltages on the input between 5 and 50 volts, then this amplifier needs to amplify its input voltage by a factor of 10, so that instead of 1 volt maximum, we have 10 volts maximum. And if we have voltages between 0 and 5 volts, then this amplifier needs to amplify by a factor of 100, so that the maximum of 100 millivolt will become 10 volts. Okay? This is the purpose of this particular amplifier, and of course, this amplifier, well, technically speaking, not this amplifier, but another circuit, when he will inform the amplifier of the amplification factor, he will also need to spit out some signals on the output, so that our Arduino will know which amplification factor we have used in this front-end circuit. Okay. Now, once we have amplified this signal to the point where the absolute maximum value is 10 volts, regardless of what we have on the input, regardless of the range that we are finding ourselves on the input, we still have here both positive and negative values. That's not okay, because the Arduino only accepts positive voltages. So this voltage from this amplifier needs to be passed through a precision full wave rectifier. Okay. I have been talking in the last month about, and I have been making 3 important videos that were basically moving forward towards this video. I have created a video about precision full wave signal rectification, and another video on peak detector circuits. I will be mentioning this in a moment, and also input offset voltage effects on instrumentation amplifiers, what I've just mentioned earlier about this offset correction that we need to do here. So I will not go into the details of how those circuits work. I will just refer to you to these 3 videos that I've done in the last month, so that if you need to understand in great details, you can take a look at them. So now, after our signal has passed through the through the precision full wave rectification, now at the output of this we have only positive voltages. And somewhere in the middle of this precision full wave rectification circuit, we can derive another signal that will basically tell us if that if the output of the rectification circuit has received a positive voltage on the input or a negative voltage. So from the output of the precision full wave rectification circuit will actually be a double output. On one hand we will have the magnitude, and on the other hand, I haven't drawn it here because it's not all that important, but on the other hand we also have another signal representing the sign, whether it's positive or negative. I will explain in a moment when we get to the actual circuit. And now we have pretty much everything we need, but we still have one small problem, which is the entire chain of signal processing up until here gives us a maximum of 10 volts at the output. And that's too much for our Arduino that needs to have only 5 volts. So this voltage from the precision full wave rectifier needs to be passed through another attenuator, another voltage divider, this time with the ratio of only 1 to 2. So from a maximum of 10 volts, it will be brought down to 5 volts, and that's it. Now we have the final voltage reference to the ground that can be fed into one of these 4 input ADC pins from the Arduino. And basically we need this circuit replicated for each channel that we want to use. Now, I have mentioned so far only the upper chain. Now let me discuss a little bit about the lower chain, because like I said, from this instrumentation amplifier, the signal follows 2 different paths. In order for this variable gain amplifier to know what gain he should apply, we need to basically have another detection circuit in parallel. So the instrumentation amplifier will send its signal, however big or small it is, to another precision full wave rectifier that will rectify that signal. This signal will be directly proportional to the input signal. Okay, this is not amplified in any way, nor attenuated beyond this point. So when the input signal will rise, so will this signal fed to this second full wave rectifier. When the input voltage will drop, so will it happen here. So here we basically obtain another voltage that is just positive, because again we cannot really work with both positive and negatives. So we are rectifying this signal once again, so that later we can pass it through a peak detector circuit, which is the reason why I studied peak detectors earlier. Okay, so a peak detector basically will generate on its output roughly DC voltage that is dependent on the peak value of whatever we have on its input, which is the signal sent by this full wave rectification. Essentially what we're doing here is to make it so that we can figure where exactly we are on the output. Are we between 0 and 5 volts? Are we between 5 and 50? Or are we above 50 volts? Okay. And based on this, we feed this signal to a comparator, well, a couple of comparators really. One comparator that compares, that has a voltage threshold associated with 5 volts on the input, and another comparator that has a voltage threshold associated with 50 volts on the input. And based on what this comparator senses on its inputs, it will trigger some switches that will in turn change the feedback circuit of this variable gain amplifier, and it will basically cause this amplifier to have higher gain when this signal on the input is smaller. And this is what it's supposed to happen. This was my logic. This was what I thought I needed to create. Now, everything works well with the exception of these switches here that are basically commanding this variable gain amplifier. And I will get to there in a moment. Now that I've explained to you, how the circuit needs to work, let me show you quickly how the circuit is actually built. So, circuit looks like this. Yes, I know it looks big, but it's not really that big, and it's not difficult once you understand that it's like a puzzle made from multiple pieces. So let's take it step by step. This 1 to 50 divider is this one here. I have placed a total of 12 resistors on the PCB so that I can play basically with different values of resistors, because we will have to measure each resistor and do some calculations on a piece of paper in order to determine the actual resistors that we will use here, because the precision of this voltage divider is very important for the precision of the entire circuit. Okay, so like I said, we have two voltage dividers here that in total, relative to a ground, this is the ground, by the way. I have placed the ground sign somewhere in the bottom, but anyway, this middle point here, this is the ground of this front-end circuit, and these are the two pins for the inputs. Basically, we are dividing by a factor of 50 the input voltage, input signal, and we are obtaining two voltages, one here and one here. Okay, depending on where we put the positive polarity of the input voltage, we will have there the positive polarity into the first op-amp or into the second op-amp. In order to make sure that no matter happens on the input, we will never exceed a safety voltage, the voltage that is safe for basically our front-end circuit, I have placed 4 diodes, protection diodes, like so, between each input pin, well, not each input pin, but each input divider, and each of the 2 protection voltage rails. I have I basically need to have plus minus 10 volts of a protection voltage that is separate from the plus minus 15 volts that we are using to power this entire circuit. And whenever the input voltage goes basically above 500 volts, and we get well, whenever we get more than 10 volts between the ground and each of these divider inputs, then the protection diodes will start to conduct, and they will not allow the voltage here to go above or below that level. This is how protection works. It's standard. You have definitely seen this kind of protection everywhere else in similar circuits, so there's nothing special about it. Now, the next block is this instrumentation amplifier. Like I said, it takes the 2 different voltages, it feeds them into a buffer each, and then with 4 precision resistors, I chose 10 kilo ohms, but it really doesn't matter all that much. The lower you go, the more current the whole circuit will draw on. What is important is that these 4 resistors will have as small tolerance as possible. Now, the smaller the tolerance, the more money you will need to spend on these resistors, because the more expensive they are. But at 0.1% resistors, they are still decent in price. Since we only need 4 of them, it's not that big of a deal. And these 4 resistors plus the third op-amp basically form a differential amplifier that will generate a voltage relative to the ground that is proportional, or not proportional, it's literally the difference between those 2 input voltages. Now, in order for this to work with smaller voltages, with smaller signals on the input, we need to overcome the input offset of this third op-amp. This is why this R2 resistor, which typically would be connected to the ground, in my case it's not connected to the ground, it's actually connected to another buffer, the output of another buffer, where we have essentially correction voltage from the positive 15 volts to the negative 15 volts. We have a couple of diodes connected to the ground and some resistors to basically pass a current through those diodes. Those rectifying diodes will keep a relatively constant voltage across their terminals. we need a correction voltage in the order of millivolts, maybe 10 millivolts or so, but typically less. So we take this voltage across, we don't know if this voltage needs to be positive or negative, by the way. So we take this voltage across both diodes, pass it through another voltage divider with a semi-adjustable potentiometer, and we feed that voltage from the middle point of the potentiometer into the buffer. And then the buffer will make sure that no matter what happens here in this instrumentation amplifier, the correction voltage stays the same. And so basically this is an adjustment that we will need to do after we have created the circuit in order for us to have a 0 or as close to 0 volts on the output of the instrumentation amplifier when we short circuit to ground both inputs. Okay. By default, it will not be 0 because, yeah, there is this this input voltage offset problem. Okay, so now going forward on the main path, we have this variable gain amplifier, which is made with another op-amp and a bunch of resistors that I have not placed on the actual PCB. I have left open to basically determine manually what values do I need, but because I have a problem with this, and I will explain to you in a moment, I basically don't know exactly what values to put here until I solve the problem. But the idea is that this is just a non-inverting op-amp, nothing more advanced than just a non-inverting op-amp. I chose TL071 because we need to have an op-amp that has a null correction ability, basically that has null pins. We would like to avoid here to use other external correction methods. So TL071 has 2 null pins. If we follow the datasheet recommendations and put a semi-adjustable potentiometer here with a smaller resistor connected to the minus 15 volts of the entire power rails, then with this potentiometer we will be able to do the null adjustment, which, similar to the other adjustment, it means that if we short circuit the input, the non-inverting input, to the ground, then on its output we should have 0 volts. And we adjust R24 here up until we have 0 or very close to 0 volts on the output. Also, we might want to place a resistor here in the feedback loop towards the ground, so that we can actually set a higher amplification, a higher gain, because then it will become easier for us to perform this adjustment, because we will be able to see voltages easily. Yeah, and like I said, by default this op-amp would not have any resistors connected to the ground, so it will work just like a buffer. I do have an R4 82 kilo ohm resistor here because I will be needing to set a gain through other resistors, and in order to not create imbalances, I have also put an 82 kilo ohm resistor here on its input. But other than that, there's nothing fancy or complicated about this. Next, we have this precision full wave rectifier, which is this circuit with 2 op-amps, 2 diodes, 3 resistors, and 1 small capacitor. I have talked about this in a previous video, so I will not explain its working again. What I will say is that besides its output, which basically will give us only a positive voltage, we can also derive here from the second op-amp's non-inverting input. We can take this signal here and later feed it into a comparator that will tell us basically if if the voltage on the input was positive or negative, because on the output we will always have positive, but our Arduino will still need to know whether we have positive or negative on the input, so that it will, you know, do correct calculations and display the voltage correctly. So this is the pin that we need to attach ourselves to in order to determine whether we had a positive or a negative voltage. Now let me show you quickly. You see now on the screen with blue the output voltage, and with yellow the voltage in this particular pin that I've shown you earlier. Whenever the input voltage was positive, we see that we have a positive voltage on this pin as well. Whenever we had a negative voltage, we see that this pin remained at 0 volts. Okay, this is why we see only basically a half wave with the yellow oscilloscope channel, because we will have 0 volts for input negative voltages and positive voltages for whatever positive we had on the input. So this is why I say we should just pass this signal in yellow to a comparator that basically compares this signal to something very, very small, like, I don't know, 10-20 millivolts. And in this way we will basically be able to tell if the blue signal is positive in that particular moment or was actually negative. Okay, now let's get back to our schematic, and last but not least we have a divide by 2 voltage divider that needs to be done with 2 resistors that also have been matched, have been manually measured. I have used 56 kilo ohms, although it doesn't really matter. 56 kilo ohms is a value that I don't use all that much. So this is pretty much what we have here on the top line. Now on the bottom line, like I said, from the inamp we need to do a rectification again of this signal directly, not passed from the amplifier, but directly of this signal. So this is why we see this particular circuit here, which is essentially identical to this one here. Okay, and then after we rectify it, we need to determine what is the peak voltage, and this is what this other circuit is doing. It looks very similar to the precision full wave rectification, but it's not. It's got distinct differences, and yeah, this circuit will basically give us a DC level that's proportional to the absolute maximum value that we have on the input, which in turn is basically proportional to the input voltage. Okay, and this peak detector voltage is fed into the inverting inputs of 2 other op amps. On the non-inverting inputs, we need to have half a volt on one op amp and 50 millivolts on another op amp. This is why I have, from my power supply, I have created a special 5 volt reference voltage that is as close as possible to 5 volts. And we have this long voltage divider made with 5 resistors. I have also hand-picked these resistors so that here I have half a volt and here 50 millivolts. Basically, whenever the input signal falls below half a volt, this first op amp will turn its output up high, which in turn should open and keep open these 2 transistors. We only need one for our variable gain amplifier. When this transistor is on and it's got its emitter connected to the ground, it should basically make a connection to the ground of these two resistors, which are placed in the feedback loop of this amplifier. And this is the way that we would basically influence the amplification factor of this amplifier. When the voltage drops even more below 50 millivolts, then this other transistor should turn on and stay turned on and pull down this other set of resistors, which will basically be placed in parallel with this other one. And based on what values we would use here, we would have yet another gain, a level of gain. Okay. And theoretically, like I said, these two resistors would not exist at all because we would not need them. We would not need to have more than unity gain in any other case. I have placed them just for the sake of having something there and making my life easier to work with the circuit. Anyway, this is where I got stuck. This is where I have noticed that the circuit is not doing well. The circuit is working perfectly up until here. The problem is when these op amps basically go low and turn off, well, should turn off these bipolar transistors by injecting by applying a small negative voltage in its base. These transistors should be fully turned off, and therefore these resistors should not be connected in any way. However, this doesn't work like this, and these transistors occasionally do get turned on for some reason, even when they should not be turned on. And when they should be turned on, they also do not work appropriately. So these transistors are basically this last point here, this rectangle here that I've drawn with a switch inside, because they are supposed to work like switches, but for some reason that I do not understand, they don't. This is particularly weird because when I tested this circuit on breadboard, it did work. It is true that I used the BC 547 transistors because on a breadboard, you know, you need to work with through-hole components. And when I manufactured this PCB, I basically replaced those transistors with 847, which I found to be electrically, at least on the internet, it appeared that these are electrically identical to 547, except these are the semi-dev versions of the 547, which is through-hole. Apparently, things are not quite like that, so I will definitely need to do a bit of research and a bit more experimentation to see, well, what's the problem and how do I solve this. Like I said, ideally they should just behave like switches when turned on and connect these resistors to the ground and change the gain of this particular amplifier. And I have placed two sets of transistors for each comparator because at the same time we will want to notify Arduino of the fact that we are finding ourselves in a different gain, a different amplification factor, so that Arduino will calculate the correct voltage on the input based on, you know, the voltage on the output, the polarity, and whatever gain we have here. This is why we have these open collector transistors. Theoretically, they should be connected to a GPIO pin of the Arduino, and yeah, based on what the Arduino reads, it would figure what voltage we have on the input. So this is what I did. Those were my results. I will show you quickly. I have started to show you earlier, but now I will show you a few results. I was playing earlier and filming this pre-recorded video, so I can show you here. With blue we have the rectified voltage on the output, which as we can see it's only positive. On the input I actually had a triangle wave at half a frequency, and it was going from positive to negative. I started from positive 2.5, negative 2.5, because that was the maximum that my signal generator could give. And at this point I was injecting the signal directly into the instrumentation amplifier's inputs, not through the voltage divider, because it wouldn't make any sense, because I would have a too small voltage and I would not be able to simulate all the possible situations. With yellow you see that polarity point in my precision full wave rectifier circuit, and I can go down to basically 10 millivolts of input signal. As we can see here, the circuit still does a pretty good job, so it is reliable, and if I manage to fix that problem with those transistor switches, then I will have a fully working voltage front end, and I will be able to continue this project. Now, I did not mention, but I mention it now, I've made some tests with Arduino. If I read all the analogic inputs and all the GPIO digital inputs, I can read them at 2000 samples per second, so 2 kilo samples per second. This should be more than enough to work with up to 200 Hertz, I would say, which in my opinion is sufficient. I will not care about working with higher voltages when it comes to AC signals, with higher frequencies, sorry, when it comes to AC signals. I don't see the point. When it comes to AC measurements, I will just want to measure, you know, what current I have or what voltage I have from my 50 Hertz network, power network, or perhaps 60 Hertz if you're in America or Japan. When rectified, this will turn into 100 and 120 Hertz. So I said, okay, I will want to work with 200 Hertz maximum. However, I've also done tests with higher frequencies, and this is what you see now on the screen. I have good results with this circuit as he is right now, up to 2 kilohertz, and from 2 kilohertz onwards, there are small problems, but it will still work up to 10 kilohertz as far as the main path is concerned, the main path that is giving on the output, you know, the magnitude. The full wave rectifier will have some problems, some small problems, that will make it so that that signal that tells us the polarity will have some distortions, some imperfections, but anyway, that matters less. Like I said, I will not use it beyond 200 Hertz, mostly because my Arduino will not be able to make more than 2 kilosamples per second of reads. 2 kilosamples per second means that I could theoretically go up to close to 1 kilohertz of input signal frequency, but anyway, I will not care about it so much. So this is pretty much it. This is what I've done. This is what I've succeeded and where I failed. I will definitely work some more on this project in the future. However, I've worked a lot so far and I want to just take a break from this, switch to something easier, and I have to admit something more useful, because this project is useful but not quite that useful. It's also more for you know, us who are passionate about electronics and having a mini lab at home, but it's not so useful for people at large, for the population at large. So for the moment I will take a break from this project, and I will come back to it later. So thank you very much for watching this. I hope you have enjoyed what I presented here. I hope you have learned something that can potentially be useful for you in the future, even if you don't want to build something like this. Please consider liking this video and maybe even subscribing to my channel if you would like to see more videos. I do my best to constantly come with new videos and build new projects, build useful things for us. Again, we are trying to prepare ourselves for the future. I'm not doing anything that doesn't make sense. So yeah, thanks a lot for watching once again, and I will see you in the next video. Bye bye.